when we're finding area with a polar function, it's going to look a little bit different than the area we found when we had rectangular and parametric equations. With rectangular functions, what we did is we found the area between a function and the x-axis. And the reason we did that is because the function gave us a value of x for any, it gave you a value of y for any x value. With a polar graph, we're actually going to be finding the area between the origin and the function. So instead of having a region that's bounded by vertical lines on the side, what we're going to be finding is going to be something that looks a little bit more like a sector. You guys remember what a sector is? So it's a slice of a disk or a slice of a pie, right? So what we're going to be finding is the area more like the area of a sector. If you remember from your geometry class, you should have found the area of a sector. The area of a sector formula, you probably did in degrees, so I converted the formula to radians. And so essentially what we do here is we take the central angle of that sector, we divide it by the total number of degrees in a whole circle. So this part right here, this fraction, this gives us what fraction of a circle we're actually dealing with. And then we multiply it by the area of an entire circle. So if this sector here was an entire circle, then this part right here, the pi r squared, would give us the area of that sector. This part right here is the fraction of the circle that we're dealing with. This expression here in radians simplifies fairly nicely. What's going to cancel out here? The pi's will cancel out. So the area of a sector in radians is actually just going to be theta times r squared divided by 2 because these pi's are going to cancel each other out. So this gives us the area of a sector. What we're going to do is we're going to do pretty much the same process, and we're not going to go through all the steps that we did with rectangular coordinates. But what we want to do is we want to take little bitty slices. And each of those little bitty slices, instead of being rectangles like we did with the Riemann sums before, now the little bitty slices are going to be little bitty sectors. And theta is going to be really, really small. So we're going to take a bunch of really, really small thetas and add up the areas of all those sectors. So since we're going to let theta get really small, this is going to become a d theta, and we're going to get this equation right here. So this integral here, it may not look like it at first, but this integral here is the same formula converted to calculus. So we have the r times d theta, or r squared times theta, which was on top of the area of the sector formula, and then we divide by 2. So to find the area of between the origin and a polar function, we're going to be using this integral. Notice in this integral here, first of all, r is written as a function of theta, so you're not going to have r in here, you're going to have whatever r is. So in the last example, we had like 2 times the sine of 3 theta or something like that. That's what would go in that part right there. And then this alpha and beta, those are the starting and ending angle measures. And so a lot of times what you're going to have to do is you're going to have to figure out what those starting and ending values are going to be to figure out what the limits on your integral are going to be.